Doing everyone's favorite, which is statics in 3D, right? Who likes this? I know when I took statics, it was very rough to adapt, very rough to understand, but eventually I did. So I'm here to actually just show you some tips, share some intuition, and hopefully help you succeed. So let's read the problem carefully and figure out what they want. Is held in place by three cables. Okay, the force acting on each cable is shown, so they show us the magnitude. Determine the magnitude in coordinate direction angles alpha, beta, gamma of the resultant force. Take x equals 20 and y equals 15. Okay, so a couple of things I realized, right? So first things first, they don't really care too much about support reactions or any type of analysis of equilibrium. All they want is, they're giving you this pretty picture, and all they want to do is, if I label these forces as F1, F2, and F3, they want to know what's FR, force resultant, which is F1 plus F2 plus F3. That's all they want to know in this problem, okay? There will be some more complicated problems where they're gonna want to know more, which is the support reactions. There's gonna be other things involved, but this is not one of them, okay? So this is really good for us to get used with 3D, and that's why I chose it, okay? So to get to it, right, there's a couple steps to dealing with 3D problems, right? The first step I'd say is you have to define 2 points of where your vector, and I'd say two known points, right? Two known / given, where your vector of interest, your vector abbreviating of interest crosses. Okay, so then you take those 2 points and its respective coordinates, and that is the coordinates, right? And what you do is you build a position POS vector. Okay. Okay. After building position vector, so after you do the position vector, you convert position vector into unit vector. Okay, and then the fourth thing is multiply unit vec times magnitude of force. Call it force I. I don't know, just force of interest or whatever it is. Whatever. The force, right? Magnitude of the force. Okay, so following those steps is crucial, right? But before we follow it, okay, I just want to explain a little bit of the intuition, okay? The intuition is as follows, right? Let's just suppose, focusing on F1, right? I should have put the arrows there. We're focusing on F1, trying to figure out which direction does this 800 vector really go, What is it? It's a cable, so it can only go in the cable direction, right? But, most problems the arrow will tell you which way it's going, right? So it's going somewhere, it's going along that direction, right? It's going in that highlighted direction, right? So if we pick those points of interest, right, which I'm just going to kind of like dot on top, right, that direction, it's part of that direction. Eventually the vector would cross them, right? Even if it doesn't immediately cross it, it will cross if you continue to, you get the idea. So you take those points and you build a position vector. So essentially, your position vector is going to end up looking somewhat in terms of length, it's going to look somewhat like this, right? It's literally going to take the whole length. It's literally going to connect B to D. If those are your points of interest, B to D will be connected, right? Now, does that help us? Not really. Just having that won't help us, right? Even though that tells us, it defines the direction for us. So the position vector defines the direction, but it defines it with the wrong magnitude. And why is it wrong? Because it's connecting D and C, right? I mean, sorry, B and D. So that's kind of wrong. It's not very useful for us. So in order to make it useful, we convert it to what's called a unit vector. So the unit vector, what it does is it just allows us to extract the direction of the position vector, and because it's called because it's a unit vector, it has a magnitude of 1. So the size of the vector itself has a magnitude of 1. And when we multiply something by something with a magnitude of 1, we get that something back. It's just in different proportions, right? Because obviously 800 is not 800 in the x, it's not 800 in the z, it's not 800 in the y. It's just 800 overall, right? It's the resultant of those three components, right? It's the magnitude. It's not even the resultant anymore. I mean, it's in a sense, it's at this point it's a magnitude, right? It's not a resultant anymore. All right, so let's just tackle it, right? Let's just do it. So analyzing F1 first. So points of interest, as I mentioned, B and D. All you do is you just start labeling which X, Y, and Z they correspond to, right? So X, Y, Z. So B is in the negative 6X, in the 4Y, and then I'm just reading this off of, this that's hidden in the back, 4Y, and then we got 0Z. There's no height, in a sense, to it. There's no, it's not going up or down, right? It's sitting in the XY plane. And then D is just 0, 0, 24, right? 0, 0, 24. Point D is sitting on the z-axis, right? So it doesn't have an x. It's not like on the edge here, or on the edge here, like having a height and some sort of side to it. No, it's straight up from 0, in that case 0, straight up 24. Okay, so it goes up by 24 in the z direction. Okay, so building our position vector, very important. This is how it goes. The tail goes first, and then the tip goes later. So it's R dB, okay? But when we construct it, we do B points minus D points. So that would be B points minus D points. So that would be minus 6 minus 0, I, because they're all X, right? Plus 4 minus 0, J, plus 0 minus 24, okay? And that ends up being plus 4J minus 24K. Okay, so when we get this, the other one, well, so we check first, we check the second. So convert position into unit. Okay, so to do that, all we have to do is just follow this little formula here, which if you've taken calculus 3, you remember. So position vector is equals to our, any vector in reality, but in this case it's, the unit vector is equal to any vector with its components divided by its magnitude, right? So now all we have to do is just calculate that magnitude, which what I'm going to do, guys, just to speed it up, not have to write too much, I'll just do it straight in my calculator. So 6 squared plus 4 squared plus 24 squared. This gives us humongous, not really, 21.06, 25.06, sorry. And this right here is just negative 6i plus 4j minus 24k, right? And by the way, what did I do is I just did square root of the I component squared, the j component squared plus, and then plus the k component squared, okay? That's the magnitude. Okay, just to let you know in case you're still not familiar with it, which is okay. All right, so now all we do is just perform, those divisions individually, right? This is going to be performed separately from this because these are different components, right? So that would be minus 6 divided by that value of the magnitude. So that has a value of minus 0.239i plus 48 divided by this value is, that is kind of weird. Hold on, it's not 48. Where did I get the 48 from? It's just 4, guys. Sorry. And the reason why I got it, okay, because I counted as 48. This is my terrible handwriting. All right, 25.06. All right, this makes a lot more sense. 0.159, 0.159 J. Beautiful. Minus 24 divided by 25.06. Negative 0.958K. Awesome. So we got this unit vector, and what we do in step 4 is multiply this times the magnitude. So F1 is finally equals to the magnitude, which was 800, times the unit vector. Okay? So what we do is we multiply each of those components individually by 800, which I'll do in my calculator to, be able to accomplish things a little bit faster for us. So we got negative 191.5 I plus 127 J minus 766 K. Okay, so we got F1. This is equal to F1. Done. So all we have to do is F2 and F3, okay? That's all we have to do now, and then just add them all together. Different color. Kind of use a lot of the black one. All right, so F2. All right, I'm going to take the picture here real quick, and let me see if I can drag it to the side. Give me a second. Okay, so if I can take it with me. Okay, brought it here. Awesome stuff, so we can analyze it as we go. Thank you. All right, good stuff. All right, F2. Analyzing F2. We have the points of interest. If I highlight it again, oops, bad job. Second attempt. Believe it or not, this is harder than it seems. All right, it kind of looks okay. So our points of interest is they are A and D, right? So D we already know, right? What was D? 0, 0, 24, and then A is simply the x which is given. I already forgot. X is 20 and y is 15. So x is 20, y is 15, both in the positive direction, and then 0 here. So our position vector is our going from D to A. So it's A minus D when we actually calculate it. Okay, so this is, by the way, this is the tail, and this is the tip. Okay, always. All right, so going from D to A. So tail to tip. Awesome. And then it's tip minus tail now. So tip minus tail is 20 minus 0, 20, I. 15 minus 0, plus 15, J. 0 minus 24, minus 24K. All right? Once we get that unit vector, I'll call it unit vector 2, RDA, divided by magnitude of RDA. Okay? Then we get 20I plus 15J minus 24K divided by that magnitude, which I, again, calculated my calculator, which is the square root, 20 squared plus 15 squared plus minus 24 squared, which gives us 34.65. Okay, so 34.65. And finally, this gives us 20 divided by that, 0.577 I plus 0.433, and then minus 0.693, 0.693. Awesome. So we can do is calculate F2, right? F2 is going to be the magnitude 400 times the unit vector. Okay, which turns out to be 400 times 0.577 gives us 230.8 in the I direction. And then 400 times 0.433 gives us 173.2 in the J direction. And the other one is 0.693 times 400, 277.2. Awesome. In the K direction. So we're good with F2. Finally, we should be able to get F3 and calculate a reaction force. All right, so I'm going to move this one more time. Okay, if I can select it. Boom. Awesome. Change colors. Easy. Highlight it for us again. We're right here. Nice. That was flawless, actually. Okay, so F3. Analyzing F3. Boom. So points of interest. C and D, right? Because they're given. There's information about them. There were others, we could pick others, but there's information about those 2 points, so we choose them. C, it's on the positive 16 for X, the negative 18 for Y, and then the 0, Z. Okay? D, same old. Okay, plus 24. Sorry. Okay, let me just go back here because that didn't look very good. Okay, so plus 24. Awesome. So we get our DC is equals to 16I minus 18J minus 24K. Okay? So unit vector 3 is equals to what? RDC divided by the magnitude of RDC, right? So we get, for the magnitude, real quick, for the magnitude, we get 34. Okay, so it's 16 over 34. This is our I component of the unit vector, 4, 7. I minus 18 over 34.53. And then J minus 24 over 34.706, 0.706 K. Awesome. Finally, multiply this times what? Magnitude, right, guys? So magnitude was 600. 600 times unit vector, which was unit vector 3. So it's 600 times 0.47. That gives us 282 in the I. Minus 0.53 times 600. 318 in the J. Minus 600 times 0.706. Minus 423.6 in the K. Awesome. There we go. By the way, I just remembered, I should have put newtons everywhere here, right? These are all in newtons, by the way. Really bad. Don't do it what I did, okay? All right, so now we just add all these up, right? Just add all these up. So force resultant is literally going to be equal to F1 plus F2 plus F3. So we're going to add i's with i's, j's with j's, k's with k's, okay? So F resultant, I don't know why I called it F3 here, is equals to, and I'm just going to kind of like highlight it and punch it in my calculator, okay? Just to save us some time. This right here plus 230, which is this right here, plus 282. Boom. So change colors one more time. 321.3 in the I, then F2. Let's kind of go the opposite way. Minus 318. Okay, go up. 173 plus 173.2. And then finally 127.2. Boom. Negative 17.6. And then minus 423.6. Highlight it. Doing the K's now. Minus 277.2. And then minus 766. Wow, that's going to be a big number. It does make sense though, because the z direction is going to fill a lot of that pole. Okay, so minus 1466.8. Okay, awesome. That's RFR. Does this tell us the answer of the magnitude? No, it doesn't. So what we have to do is we just take this and we square it, right? This time I'll show that middle step just because, I don't know, I think I didn't do it, so I'll do it this time. So this is just the magnitude of FR, okay? Because that's what they're looking for, by the way. They wanted this, okay? So that's the square root of previous answer squared plus 17.6 squared plus 1501.7. And that is in newtons, guys. Forgot it again. Promise I don't forget on my exams, but I'm forgetting it now. Okay, so this is the resultant force, right? We're not done. Okay, we're not done. They want the alpha, beta, gamma angles of this force resultant. So what is alpha, beta, gamma, right? Alpha, beta, gamma is basically, let me just draw a coordinate system here real quick, and I'll just put like a random force, right? Let's just say it's a random force. Let me change colors, right? So it's a random force, right? X, Y, Z, random force. What is alpha, right? Alpha is the angle that's formed between this straight to the coordinate x, okay? What is beta? Straight from here, you guessed, to the positive y. By the way, it's always the positive, right? Because otherwise I could go technically to the projected side and the back. So it's the alpha goes from the vector to the positive x, the beta goes from the vector to the positive y, and you guessed it right, gamma it's to the positive z, okay? Essentially, literally what we're calculating though is, if I may further explain on this, cosine alpha, cosine beta, and cosine gamma literally are exactly the same thing as the unit vector that we can calculate, which we will, in the I direction of, you know, any force or any vector, right? If you want to find what's the alpha, literally all you do is just do cosine inverse of that component in the I direction, okay? Of that component of the unit vector, I should say, for better clarification, in the I direction. Same thing applies for beta, and same thing applies for gamma. So all we're going to do is figure these bad boys out and then take the cosine inverse of them, and then we'll get the angles, okay? So it's the same thing. Let me just write it down for completion here. This is alpha, beta, and this is gamma, okay? So we have the magnitude, right? This is what we're going to need. We're going to need this, and we're going to need this, because remember, the unit vector is going to be equal to, so I'll call it unit vector R for resultant, right? It's going to be 321.3 I minus 17.6 J minus 1466.8 K, all divided by the magnitude, 1501.7, and this is all in newtons, right? But it will cancel the units. So what this is going to do, this is going to extract the direction of our force resultant, right? Which is essentially what these angles are. They're the direction of that vector in 3D, right? Okay, so we can calculate this. This is going to be equal to 1.3 divided by 1501.7, boom, 0.214. I'm going to round a little bit, okay, guys? 0.6 divided by 1501.7. Just in case you're double checking the answers with the solution manual, mine may be a little bit off just because I've been rounding a little bit. 0.01172, okay, J minus 1466.8 divided by 1501.7, 0.9767K. Okay, so now what I said is we're going to take this value and we're going to plug it in the inverse. Okay, so I'm even going to highlight it in different colors. Look, this value here, okay, this value with the negative, please, here. And then the negative is very important, by the way. It changes completely the angle, right? Right there, okay? So I'm going to do that for us. So I'm going to do cosine inverse of that first one, and then we get 77.64. And so alpha degrees, and then beta is equals to, bear with me 1 second, 90.67. I'm sorry, this is not good. And then gamma so that's a negative angle. Why didn't it give me? Oh, it's past 90 degrees, so we're good. Okay, it's not supposed to be a negative angle. Okay, okay, then inverse cosine. 1 second. Almost got it for us here. All right, I think I actually got it all, guys. So 167.6 degrees. Literally took us a little while, but I hope that this gives you more clue when you're navigating through your studies of how to approach a problem like this. So a quick recap before we wrap up, right? These steps that I showed you are going to be extremely, extremely important for solving 3D problems, right? If you don't follow these steps, I mean, I don't see how else you're going to solve 3D problems, right? I mean, there are some where you can do it the scalar way, which you will learn later. There are some where you can deal with double projection, which will save you some time. But for the most part, it's always best to at least know this, because this is what's called a safety net, right? Every category, every possible category could fall under this type of approach later in the future. So if you know this, you're basically setting yourself up for success for multiple types of questions to come. Okay? So please go over this. Please, take notes. Try it on your own. Come back, pause, And I hope that this helped, okay? If it did, please let me know. And if you want more help, if you want more videos and different kinds of videos, also let me know, okay? You guys take it easy and have a good one. Take care. Bye.